Hi there and welcome back. We are going to do two more sample problems regarding these integration methods, and after that we will discuss the introduction to the other method called the superposition method. Okay, so this second problem that we have is taken from the textbook by Beer and Johnston and D. Wolf, and the problem is actually almost the same as our first sample problem. I mean, in terms of solutions on the procedures, it's almost the same, except that we have a different types of beam conditions. Right here we have a simply supported beams, and it is under uniformly distributed load. So right here I have already prepared the entire solution, so that to save time, because the next sample problem that we have, we are going to solve it, and it will also consume a lot of time. Okay, so as what we did, the first step that we did was to solve for the moment equations. So before we can do the integration, then we really need to find the moment functions. Okay, that's the moment equation. And how do we find that moment equation? Is one way is to find that by making a section cut. Okay, so right here, we made a cut, and actually that's a representation anywhere along the beam length, because we have we use an arbitrary distance x. Is that means at any distance along this beam loadings, or anywhere along this segment between A to B, because it's just simply the same. Okay, so it's a moment function. So we made a cut, and then we expose the internal forces, the shear force and the moment force, and of course we also have to determine the reactions at A. And the reactions, actually, if we base it from this beam conditions, it is symmetrical, and therefore half of this distributed loadings will be carried by this support, by this roller support at B, and then another half will be carried by the beam support at A. Okay, so that's how it works if we have a symmetrical loadings, and also in terms of the lengths or distances. Okay, and the value here is just simply 1/2 of the distributed load okay, so 1/2 of the distributed load times the length, because the unit of distributed loading is load per meter, or load per unit length. Okay, so we have to multiply that by the length so that we can obtain the unit of a load. And since this is a distributed loadings, then we can also express that in terms of its resultant, and the resultant force actually acts at the distance x all over 2. Okay, so from the section cut to this point A, we denote the distance x because it's an arbitrary distance. Okay, now that we have this, then we can apply the summation of moment at this point, or anywhere that will also work, but for me I use this point as my center of moments. Okay, so I take moments, the moments produced by this reaction force at A, and the moment produced by this external loadings. Okay, and the distance is x all over 2. Of course, this is x, so if this is x all over 2, then this is also x all over 2. And also I have to take into account the internal force, the concentrated bending moments. And when I apply that, then I obtain this equation. It says here that m is equal to the negative omega x squared over 2 plus 1/2 omega lx. So you would notice that the moment function is of degree 2. Okay, so after we obtain that, then we substitute the moment equation or the moment function to the moment deflection um, differential equations, and we will do integration, or we will integrate it twice. Okay, so we just substitute and we did integration. And take note that whenever you do integration, we will get an arbitrary constant, unless we have, or we substitute the boundary conditions as the limits right here. But sometimes it's just hard to find, so that's why this is the general way for finding the particular solution. But that will also work actually, if you have the limits, or if you know the limits, or if the boundary conditions are direct, then actually you can also use that. Okay, so we integrated and we obtain an arbitrary constant, and the number of arbitrary constants actually is the same as the number of how many times you perform that integration operation. Okay, so since we did integration twice, then we get two integration constants. And right here, if you simplify the general solutions, we have this. So we need two boundary conditions in order to solve for the C1 and C2. Okay, so right here, the boundary conditions of this beam condition is at x is equal to 0. So right here, at x is equal to 0, the deflection right here is 0. Okay, again, why? It's just simply because there is a reaction force here that it doesn't allow any deflection. And the same is also true at this point B, at this roller support. So the roller support, so from this reference points, here's our reference point. So the x distance here is x is equal to the length, so x is equal to L, and again the deflection is 0. So if we substitute this, let's say here's our first boundary condition, if we substitute this to that equation, then we can solve for the C1 or either C2, and also we have to apply this to that equation. Now the difference from the first problem that we have is we took boundary conditions only at the fixed support, because the other one is a free end, and whenever we have a free end, there's no boundary conditions there. So at the fixed support, we utilize also the slope. Okay, and of course if you use the slope, for example the x and the slope, then you have to substitute that x value and the slope value to the slope equations. Okay, so to this first integration expression. Okay, so after that, so we obtain the value of C1 and C2. C2, by the way, is 0, right? So at x equal to 0, the deflection is 0, so this C sub 2 is equal to 0. And for C sub 1, we have this expression. Okay, so now we substitute all the C1 and C2 to this equation, to the general solution, and then we obtain this particular solution of the deflection curve, or of the elastic curve. Okay, so what this means is, if you have this expression, then that means that you can find the deflection at whatever x distance. Okay, so these are just arbitrary, the omega, but of course when we do the mathematics, we assume this as a constant. I mean a constant value. Okay, so here's our expression, and we are asked to find the maximum deflection, and that maximum deflection actually occurs at the midspan. Okay, so right here we have to draw this figure, and the maximum, I mean intuitively we know that this maximum deflection occurs at the midspan. Then if it's at the midspan, then the distance would be simply L all over 2. Okay, so meaning that if we substitute this L over 2 to the axis right here, then we can obtain the maximum deflection, and it's right here. Okay, so here's our equation. So if you have this EI, if you have the length, and you have this omega, then you can substitute that and you can get a defined value or magnitude. Okay, so I think that's all, and we'll move on now to our next sample problem. Okay, so this next sample problem is still taken from the textbook by Beer et al. And it says here that for the beam shown, determine the equation of the elastic curve, the slope at end A, and the deflection at the midpoint of the span. So right here we have these beam conditions. We have point A and point B, and we have the length right here. And the loading is given in terms of actually it's a higher degree. I mean it's a nonlinear equation for this load function. Okay, so in this case, if we cut this section, we cannot actually or it would be not convenient anymore to make a cut section. Like for example, if we cut here, then how would you know the centroid for which the resultant of this load distribution acts? Okay, so that would be less convenient for us, I mean in terms of mathematics. So the other way to solve for this, again, we still want to obtain the moment function. Okay, so the other way is to integrate this load function twice so that we can obtain it. So that we can obtain the moment equation. So recall that we have this relationship that if you integrate the load, what you get is the shear, right? And if you integrate the shear, what you get is the moment. And if you integrate the moment, what you get is the slope. And then after that, if you still integrate this, then what you get is the deflection. Okay, so recall this relationship. Okay, so here's the integration, and if we do the reverse, that's gonna be a differentiation. Okay, so here this load is given in terms of function, so we just have to integrate this so that we can obtain the moment equation and substitute that to the moment deflection equation, and then we can finally solve for the deflection. Okay, so for the solution, okay, so that's right here. Okay, so let's equate first. All right, equate the load function to the shear derivative. Okay, so what that means is that recall this expression that the load is equal to the negative of the shear of the derivative of the shear. Okay, so recall that because this one is given, so we have to take into account this negative sign. So therefore, we can rewrite it as dv all over dx is equal to, if we transpose this to the left hand side and we substitute this expression to this, what we get is actually negative. Okay, so let us just rewrite for now. Okay, x all over L minus x squared all over L squared. Okay, so let's arrange this in order, meaning that the higher degree would be right here. Okay, so that means that we can take this out, this negative sign. So what we get is 4 omega initial is equal to x squared all over L squared minus x all over L. Okay, so here it is. Okay, so that's it, right? That's the derivative and the load. Okay, so the next is integrate. Okay, integrate the equation to actually the shear equation to, actually no, it's not the shear, this is still the load, right? The load equation to obtain the shear, right? To obtain the shear. Okay, so let's do the integration. dv all over dx, let's integrate this. Okay, is equal to 4. Okay, this is integral of x squared all over L squared minus x all over L. Okay, times, of course, this dx, integrate with respect to x. Okay, so sometimes I write it here dx because if I perform the integration to both sides, then I just have to remind myself that there's going to be dx right here. Although in some notations they don't use this. Actually, you can trace that back to the history, that when Leibniz used these equations, it's there was a time that he changes this, that the derivative is in terms of the ratio of the differentials. But at first, it's taken as one quantity as the slope, but later on he changed it to the differential, so it's something like you can separate these two. Okay, anyway, let's go back here. So what's the derivative of this shear? Then this will just be, I mean, integral of the derivative, then it's just going to be the shear is equal to 4 omega is equal to this L squared. This is actually taken as a constant, so that's going to be L squared, right, times the integral of x squared. This is just x cubed all over 3 minus 1 or all over L, okay, times the x squared all over 2, right, plus c sub 1. Okay, so the next is, what else? Integrate again. I guess we just have to integrate again to obtain the moment function. Okay, so if we integrate again, we have here v times dx. Okay, so let's just rewrite for now, and we have here 1 all over L squared times x cubed all over 3 minus 1 all over L times x squared all over 2, right, times dx plus, of course, c1 times the integral of dx. Okay, so let's do the integration. So right here, this becomes the moment function, and this one for omega, then the constant would still remain 1 all over L squared, right, and this is gonna be x cubed, right, so that's gonna be x to the 4, and the n right here, n times this 3, that's gonna be 12. Okay, so x to the 4 all over 12 minus 1 all over L times x cubed all over 6, okay, plus c sub 1x plus another integration constant. Okay, so here it is. Here's our moment function. Okay, so the next step is to apply the boundary conditions to solve for C1 and C2. Okay, so take note, apply the boundary conditions. This is referring to the, if we will use this moment function, then of course we need to find the boundary conditions in terms of the x and the moment. Okay, so right here you would see that the boundary conditions here, this is x is equal to 0. So what's the moment at this support, at this plane support? The moment right here is just 0. because the pin allows rotation. So right here would be 0. And right here at x is equal to L, what is the moment? It is still the same. M is equal to 0. So here's our boundary conditions, and we need to apply this to this moment equation. Okay, so at x is equal to 0, M is equal to 0, and therefore let's substitute this to this equation. What we get is equal to 4 and 0 minus 0, okay, plus 0 plus c sub 2, and therefore c sub 2 is just equal to 0. Okay, so the next is at x is equal to L, another boundary condition. At x is equal to L, M is still 0, so therefore 0. Let's just substitute all the x's with the L. L to the 4th, 12 all over 12 minus 1 all over L times L cubed to the 6th, right, plus c sub 1 L plus 0. And if we do the simplification, what we get is c sub 1 is equal to 1/3 L, right? So that's it. And therefore, if we substitute, okay, substituting, okay, C1 and C2 to the moment equation, okay, what we get is M is equal to this expression, right, times x to the 4 all over 12 minus 1 all over L x cubed all over 6, right, plus 1/3 of this omega times L times x. Okay, now once you have this, right, once you have, here's our moment function, but of course this is a particular solution. So that means that there's no more integration constants. Okay, so now once you have this, then you have to integrate this twice in order to obtain to the deflection equations. Okay, so let's just simplify it here or fast forward, but I'll just write it here. Integrate the moment function twice to obtain the deflection. Okay, and what we get is something like this. Okay, so from x to the 4th, what we get is going to be x to the 5 plus another integration, so that's going to be x to the 6th, right? So x to the 6th, and right here will be 360, okay, 1 all over L, then x to the 5 all over 120, okay, plus the integration, not yet, this third term, plus c sub 3 times x, okay, plus c sub 4. Okay, so again there exists another set of arbitrary constants, simply because we did an integration operation. Okay, so we need to solve this. So how do we solve this integration constant, arbitrary constants? We need the boundary conditions. Okay, and the boundary conditions must be in terms of deflections, because if we are going to substitute the boundary conditions, because this is a deflection equation or deflection function, then what we need are boundary conditions regarding deflections as well. So going back here, our deflection, so at x is equal to 0, m is equal to 0, and deflection, we know that there's no deflection right here, this is just 0, and right here the deflection is also 0. Okay, so let's substitute. Okay, so if we substitute this, or solve for substitute arbitrary constants, boundary conditions to solve for c sub 1 and c sub 2. Okay, and if we use this at x equal to 0 and this deflection is equal to 0, we get c sub c sub 4 is equal to 0. And if we use another boundary condition at x is equal to L and the deflection is equal to 0, what we get is c sub 3 is equal to negative 1 all over 30 omega L cube. Okay, so that's it. Okay, so after that, since we have the C4 and C3, then therefore we can just write the expression for the deflection. Okay, this deflection is equal to, sorry, I forgot that there must be, I think there must be an EI all over here, right? EI, and right here should also must have E sub I. Oh, sorry, not E sub I, E times the I. Okay, so the expression now is this one, 1 all over L squared times X. We just have to copy this and just substitute the values of what we got, the values of C3 and C4. So this is X sub 6, 360, okay, minus 1 all over L times X to the 5. This is 120, okay, and plus 1/3, right? X cubed all over 6, okay, minus 1 all over 30, okay, all cubed times X. Okay, so here's now our expression, right? Let's write expression for moment deflection, moment and deflection. Okay, so what we are asked is, or the equation of the elastic curve. Okay, look at this right here, elastic curve equation. Okay, so we are asked here that we are to find the equation of the elastic curve, and this is already done. And let's find the deflection at the midpoint of the span and also on the slope at A. So once you have this, then you can just substitute the values in order to solve for this. Okay, so let's solve here. The deflection at midspan is when X is equal to L all over 2. Okay, because this is symmetrical, then the deflection right here would be at the midspan, the greatest deflection. Okay, so we can just draw it here. If I think it's also nice if we draw it here, the deflection curve. Okay, so if we substitute this L all over 2 to all the x's right here, what we will get is this expression for the delta max. Delta max is just equal to negative this is negative 61 all over 5, 760, right, times the distributed loadings times L to the 4th all over EI. Okay, and what this means is that if we have this negative sign, it just simply means that we are going downward. Okay, By the way, I forgot to write here this quantities, this 4 times the distributed loading, so there must be 4 times this omega, not that is 0 or initial. Okay, so that's it. And here's our maximum deflection, and lastly, to obtain the rotation of A, okay, we just need to use x is equal to 0, right? So if here it is, our beam, and here's our deflection curve. So right here, the rotation right here, okay, so that occurs at x is equal to 0, then theta will be will have some values. Okay, so let's substitute that, and what we obtain is this theta is equal to negative this omega times L cube over 30 EI. Okay, so that's how this integration method works. Okay, so I guess I have fast forwarded some of the lines or the steps. It's just simply because we don't have much time, but I think you already know the idea or the procedure regarding this integration methods. So all you need to have is to obtain the moment functions, and once you have that, then you just do the integrations and then apply the boundary conditions. And once you have this expression, then you can actually solve anything. I mean, you can solve the deflection at any point or anywhere along the length of the beam. Okay, so that's it, and in the next video we will discuss the next method called the method of superposition. Okay, so see you in the next video.